So we were looking at the integers modulo n and showing congruence modulo n. We looked at some properties of congruence mod n. And what we want to do now is define what a congruence class is. What is a congruence class modulo n? So let's say you have integers a and n is a positive integer. So that means n is greater than or equal to 1. So the congruence class of a mod n, and the way we denote that with a and square brackets around that. It almost looks like a box. And then our book just puts a in square brackets, but I put a little subscript n because I like to indicate this is mod n with that subscript. So a congruence class mod n is defined by the following. It's the set of all integers b such that b is congruent to a mod n. So basically, the congruence class of a mod n consists of all those integers. It's the set of all those integers that are congruent to a mod n. So everything that's congruent to a mod n is in the congruence class of a mod n. So that's our definition. So what I want to do, I want to make a little note here. So we have the definition that the congruence class of a mod n is equal to all those integers b such that b is congruent to a mod n, right? That's our definition. And that's what I have written here. Now we can rewrite this a little. What does it mean for b to be congruent to a mod n? Well, it means, by definition, n divides b minus a, right? N divides b minus a. That's what it means for b to be congruent to a mod n. So here I have my second way to write this set in the brackets. Now, let's unwind that a little. Unwind, what does it mean for n divide b minus a? Well, it means that b minus a is a multiple of n. So b minus a is n times something. So k must be some integer, right? B minus a is nk, where k is some integer. Well, I can basically say this is the same thing as saying all the integers b such that if I get b by itself, add a to both sides, I get b equals a plus nk, right? A plus nk, where k is an integer. So before the such that sign, we have those integers b, and after the such that sign, we have b is of the form a plus nk, where k is an integer. We can just replace the b altogether in front there before the such that symbol with a plus nk, right? All the b's are of the form a plus nk, so we'll say this is all integers of the form a plus nk, where k is some integer. Now this is the most useful form right here that I'm putting in this red box. Well, that's not red, is it? Let's make it red. In this red box right here, what I have, this is probably the most useful form of describing the congruence class of a mod n. So let's just follow up on this description. This is abstract. Let's look at in a specific example. Let's say examples here. Example. I'll do my first example here. Let's say I look at the congruence class of 3 mod 7, the congruence class of 3 mod 7. Well, if we use this red characterization, it's everything of the form 3 plus 7k, right? Such that k is an integer. So here 3 is a and 7 is n, so I got 3 plus 7k, k is an integer. So basically what we're saying, you can let k be anything it wants to be. K can be 0, 1, 2, 3, or k can be negatives 1, negative 2, negative 3, and so on. So if k were 0, I get 3. If k were 1, I get 10. If k were 2, I get 17. If k were 4, no, I'm sorry, if k were 3, I would get, let's see, k were 0, I get 3. K were 1, I get 10. K were 2, I get 17. K were 3, I get 24, and so on and so forth. Okay? Now we could also do negative ones for k. K could be negative 1, you get negative 4, and negative 2 would give you negative 11, and negative 3 for k. What would negative 3 for k give you? I believe negative 18. And so on and so forth. Dot, dot, dot. Yeah. So all of those integers there we've listed, they all belong to the congruence class of 3 mod 7, all of those. So it's a set of integers, that's what it is, congruence class. Let's do the congruence class of 4, and let's go mod 6, So by this red characterization here, it's going to be everything of the form 4 plus 6k, where k is an integer. So you can let k be 0, 1, 2, 3, and so on, or -1, -2, -3, and so on. So that'd be like 4 if you plug in for 0. K could be 0, you get 4. K could be 1, you get 10. Then you would get like 16. And then you would get like 22, and so on and so forth. Or you can use -1 for k, in which case you're going to get -2. You could put in a -2 for k. It's going to give you -8, and so on. Let's see, we could plug in a -3 for k, and we're going to get a -14. And so on, dot, dot, dot. Okay. So get the hang of what these congruence classes are. They're sets of numbers, and they jump up by the modulus. So in number 1, the modulus was 7. So there's a space of 7 between the numbers. In number 2, the modulus was 6. So there's a space of 6 between all the numbers. Okay, so here's theorem 2.3, which is next. Really important theorem that's going to probably be used occasionally. It'll be used some in this unit, chapter 2, and it'll be used probably in later units. This says that the A is congruent to C mod n. A is congruent to C mod n. If and only if, the congruence class of A mod n is equal to the congruence class of C mod n. So on the left side here in red, we're talking about things at the elemental level, at the integer level. So an element A is congruent to an element C, so an integer A is congruent to an integer C, mod n, if and only if a set is equal to a set. A set is equal to a set. So remember, congruence class of A mod n is a set, and the congruence class of C mod n is a set. So the red side is at the elemental level, the integer level. The right side is at the set level. So we want to prove this. So I'm going to start by proving the forward direction. I'm going to suppose that A is congruent to C mod n. Now, what does that mean? Well, let's not unravel any definitions just yet. Let's try to focus on proving the blue. So we will show that these two sets are equal. So how do you show two sets are equal? So you have to go back to your transitions class. You have to show that one is a subset of the other, and the other is a subset of the other. So we're going to show that A's congruence class mod n is a subset of C's congruence class mod n. That'll be part of it. And after you do that, we're going to show that C's congruence class mod n is a subset of A's congruence class mod n. So show that each set is a subset of the other. A's congruence class is a subset of C's congruence class. C's congruence class is a subset of A's congruence class. Okay, so we're going to start with the first subset inclusion. We're going to start with something in A sub n. So let's call it B be an element of A sub n. So let B be an element of the congruence class of A mod n. We want to show that B is also in the congruence class of C mod n to show the first subset inclusion. Well, what does it mean for B to be in the congruence class of A mod n? Well, it means, by definition, B is congruent to A mod n. So if we put this statement here, well, this statement here, and I'm underlining with this statement, those two underlined statements. So notice that they both have an A here. So you have B is congruent to A mod n and A is congruent to C mod n. Then by what's called transitivity, B is congruent to C mod n. Let's just do a little scratch just to show that scratch. right? So we had B is congruent to A mod n, and we had that A was congruent to C mod n, right? So these matched in the middle, so our conclusion was that the outside, B, is congruent to C mod n. That's the transitive property for the equivalence relation for congruence mod n. Okay, what does it mean here? If B is congruent to C mod n, well, what does that mean? That means that then B is an element of the congruence class of C mod n. That's what that means. So we have shown the first subset inclusion. We have shown this that I checked off. We have shown that A's congruence class is a subset of C's congruence class. Why? Because we start off with an element B in the congruence class of A mod n, and we were able to show that B is also in the congruence class of C mod n. That gets us this first check mark. Now the second thing we need to do is do the second check mark I'm just writing down, that the congruence class of C is a subset of the congruence class of A. So let's see if we can do that. So what I need to do that, I need to get that, I need to start off with a B and the congruence class of C mod n. And I want to show that that B is also in the congruence class of A mod n. Well, if B is in the congruence class of C mod n, that means B is congruent to C mod n. Okay? Now, what I'm going to do, I'm going to use the symmetric property. By symmetry, so we know that this congruence relation is symmetric. We can flip the B and the C. We can say C is congruent to B mod n. And then from there we can use transitivity again. So remember at the very beginning in red we had A is congruent to C mod n. And now we have C is congruent to B mod n. So from these two, we can conclude that A is congruent to B mod n. Why? Because these two in the middle match. This is using transitivity. So I'm going to say here by transitivity, and now I'm back to my proof. Transitivity A is congruent to B mod n. Well, what does that mean? That means that we can use symmetry, again, by symmetry. We can flip the A and the B, and we get B is congruent to A mod n. And what does that mean? That tells us, thus, B is an element of the congruence class of A mod n. So we started off with B as an element of the congruence class of C mod n, and we're able to show that same B is an element of the congruence class of A mod n. So that tells us precisely the second check mark right here, that C's congruence class is a subset of A's congruence class. So that shows the forward direction, right? If you got the two subsets, then A's congruence class and C's congruence class are the same. So now we want to start with the blue. We want to work backwards. I'll do my backwards proof now. Let's suppose A's congruence class mod n is equal to C's congruence class mod n. So what do we want to prove? We want to prove the red, that A is congruent to C mod n. So right now we're at the set level, so we want to get to the elemental level. So we're going to take an element of one of our sets. Let's take, let's call it B. Let B be an element of congruence class of A mod n. But wait a minute, A's congruence class is equal to C's congruence class by assumption. Now what does it mean for B to be in the congruence class of A mod n? Well, it means that B is congruent to A mod n. But also, B is an element of the congruence class of C mod n, because A's congruence class and C's congruence class are the same. So B is in the congruence class of C mod n. That means B is congruent to C mod n. So what we can do, we can use symmetry right here. So by symmetry, A must be congruent to B mod n. I'll do a little scratch work here on the side. So what do we have? We have A is congruent to B mod n in yellow. And red, we have B is congruent to C mod n. So putting those together, that implies A is congruent to C mod n. That's by transitivity. So there's my scratch work. So let's say by transitivity, A is congruent to C mod n. And that's what we wanted to prove in red, right? A is congruent to C mod n, this one. And that's it. That's our proof, both directions. All right, I think we will stop with that.